greetings. In this one, we will explore the idea of convergence / divergence in the context of this infinite series. And what the infinite series, by the way, is basically a sum of all these things as we gradually plug in 0, 1, 2, 3, and then all the remaining positive integers until as big number as we want. And if it converges, then these terms will eventually get very small incrementally, and then as we take the limit of this term, where we plug in infinity for this, then that should approach 0, and then it can be convergent, and the possibility of convergence of this entire series is possible. But what I want to figure out here is whether if it's convergent, and I also want to use a concrete test for it. There's various tests to determine the convergence / divergence, or at least to point at the indication of whether it's going to be convergent or divergent. Sometimes these tests will have several possible results, ranging from definitely convergent to definitely divergent, and between that it can be indeterminate. So when you get a particular result, even in that used test for convergence / divergence, you then are basically redirected to further look into the example, because at some values, actually, even the test's results will not suffice to tell you whether if the series actually will converge or diverge. But in this case, I have it prepared, and in this case I have it prepared, I already know that the result will not involve that such scenario, and what it will involve is it will be either convergent or divergent. I can already say now. But let's leave the result to the end of our calculation, and let's also explore the way we're actually going to get to it. So as I said, there's many tests, and they're all learned as part of the calculus curriculum or something like that. Doesn't necessarily have to be so, but one usually learns them as part of that curriculum. But regardless of that, there's many tests, and the test that we're going to use in this case is called the ratio test. So this is basically an infinite series, and what it is a series basically is the same thing, similar idea to a sequence. Sequence are terms where basically this is a function, but we only put natural numbers there and 0 perhaps. And in the case of series, we add them all up. So if it's infinite series like this, we add all the options from 0 till infinity, all plug in here, and all these terms with all these different plugged in positive integer values, / natural number values, we will add up all these terms. But in this case, I'll just use the test that is to be used in this case. And by the way, very often these examples pop up, and they're quite common. Some exponential function in a fraction, in a quotient with some factorial. Yes, here we see all the same variable, and yes, actually very often it happens that this test that I will choose now will be practical in such cases, especially when we see a division. Then a ratio test tends to be quite useful often. And now to introduce how to use it and what a ratio test really means. So basically, with a ratio test is we look at this argument here. We don't regard the series, as often is done with tests for convergence or divergence of a series, and we take a particular limit, and the limit is as follows. There's the limit taken of, and let me say, okay, usually it's with n there. I have case here, so I'll do it with case. I can just keep using the same letter, although it's often switched or used another letter. Doesn't matter. In this case, I'll just use the k. Case goes to infinity. And what is the limit? Well, it will be the limit of a sub n plus 1 over a n in an absolute value. And then it will be equal to something. But the point here is that it must be an absolute value, and it is the quotient, the fraction between one term over the previous term. And of course, let's say as infinity, so what this theoretically could mean is the very last term over the term before, right before the last term. And well, in practical sense, if we wanna then use it for this concrete thing here, is what we will basically plug in is, we'll first plug in k plus 1 instead of k, and then we will divide it by this expression as it is. So what I'll do here is I'll just use this very definition of this test, this is the ratio test, and I will use it for this scenario, and eventually we will get somewhere. It will be practical and it will be used in this context. So as seen here, I will do the limit as k approaches infinity of the absolute value of a n plus 1 over an. So arbitrary term divided by the term preceding right before it. And as obvious from what has been said before, all these terms are generated by plugging in a natural number here. So right before it is integer exactly 1 unit less. Easy as that. So we have to actually write it in a general form. So actually the fraction will not be very space efficient to write here. I'll use this division symbol instead. But in any case, what it means is, if you want to do n plus 1, then instead of k, I will always do k plus 1. So 2 to the k plus 1 over k plus 1 factorial. So what I did, I took this expression and just replaced every k by the expression k plus 1 inside all places where k appeared. And then I divided by the term preceding it. So basically k plus 1 minus 1, or as I said, basically this term. So it is basically this argument dividing an argument 1 unit ahead of it, or evaluation of this argument 1 unit in front of it. And so now we can play with this further and actually get to some result eventually. So we will use some limit properties, which I will not actually explicitly mention in this video, as the main point of it is to actually introduce the use of the ratio test in this context. So how do I rewrite this? Well, division, I will switch this fraction first. So I can still write this 2 to the k plus 1 over k plus 1 factorial divided by, well, instead of division, I'll do the multiplication, switch the fraction. And now I'll make this equal to some rewrite form. And here is where the magic will start happening, because thanks to this use of this ratio test in this context, in the context of such an argument, we'll have a lot of things cancelling out. Thanks to the fact that this was a fraction, and then because of this division of fraction per fraction, a lot of things will cancel out, especially thanks to the exponent properties, as well as the properties of how the behavior of factorials plays out. So that will help us actually. Now, how can I write this? Well, I want to get the same thing in the numerator and denominator. Well, I can get this and this somehow connected. So I will rewrite the whole expression. By the way, when we multiply fractions, we can have it as one fraction where all the things up and below are multiplied by each other, just to visually simplify for now already. So there's that. And now I will rewrite this as 2 times 2 to the k, because that's the same, like, I can also write it like this, so it's even simpler to understand. If I have added exponents, I can multiply the exponents broken out into addition of to eventually make up for that whole value. So 2 to the k times 2 to the first is the same as 2 to the k plus 1, exponent properties. Then times k factorial, that's the whole numerator. The denominator will be taken care of as follows. It will be k plus 1 factorial, but what I want to do here is also something similar like we did with these two in relation to each other. Because this 2 to the k already will get cancelled out by this newly separated out 2 to the k here. So that's one step forward. And then k factorial, what it basically means is k times k minus 1 times k minus 2 until that is 0. And so with this case, this can be written as k plus 1 times k factorial. So it's no longer k plus 1 all of that factorial, but it's k plus 1 times k factorial. Now things can be cancelled out using the factorial properties. This with this, and this using the exponent properties we also could rewrite, and so things are cancelled out. What we have now left is a very simple limit. So what we have is a finite constant 2 divided by a linear function where we have almost unchanged, k will be infinity, so almost unchanged infinity in the denominator here. Well, 2 divided by infinity should be 0. So the result of this limit now is 0. And what does this tell us? So there's a few options for the ratio test. So the ratio test, as we see it here, with this absolute value and so on, in this case the absolute value was not necessary because the result ended up being 0. So there's no dispute between it being negative or positive. If something ended up negative, then of course it would be made positive by the absolute value. If it ended up being positive, then it would not. If it ended up being negative, would be made positive by the absolute value. If it ended up positive, would not be changed, of course. In the case of 0, there's no dispute in that context. But in any case, we got 0. And the ratio test, as some other tests, has the property that we have to now evaluate what it actually means to us in the context of what result we got. So the rules are as follows. I can just write that in this case, so I'm writing for the concrete example of this argument, or I can just leave this general formula, but actually I'll write it in this case. So we just got this result, that limit of 2 to the k plus 1 over k plus 1 factorial, all that in the absolute value of course, divided by 2 to the k over k factorial is 0. And now, there are some values that this can have, of course. So what are the values? If the limit, so I will just do an arrow, if the result ends up being smaller than 1, then that means that it's convergent. So actually from this we now know that this series is convergent. If it's equal to 1, then it's not determinate. So not determinate. So still some more work has to be done to actually find out whether if it converges or diverges. And then if it's bigger than 1, then it's divergent. So that's the rule. And it also makes sense from a standpoint of, from a general standpoint, if one thinks about it. Then of course if we want convergence, we want the terms to be decreasing, and actually at the very least if this is below 0, then of course the next term is smaller than the previous term, which implies that the terms are decreasing. And if that happens even at infinity, that still the term is smaller than the previous one, then that implies convergence here. So thereby we showed that this infinite series is convergent.